This week we're going to talk about bonding. Now, bonding, I've kind of addressed a lot of these concepts as we've gone through the course. But this is a nice place to kind of begin to put it all together for you with the addition of actual molecular structure and how that plays out. All right, so we have ionic and covalent bonding. So remember, an ionic bond is when you basically have a metal that loses electrons to become a cation, and a nonmetal that gains those electrons. So a great example of that is whenever you have Na, two Na atoms, sodium atoms, that are going to react with a Cl2. When that happens, then you produce two NaCl. So this is a nice redox reaction, because now then the sodium on the right hand side has a positive charge, whereas on the left hand side it's a zero charge. The chlorine on the right hand side now has a negative charge, and the chlorine on the left hand side has a zero charge because it's in its elemental form. So what we formed is a nice ionic bond between each of those NaCl's. Covalent bonding is when you have two nonmetals that combine to form a covalent bond. So a great example of this might be where you have a carbon, as in graphite or a charcoal briquette, that'll react with O2 whenever you add a little bit of heat to it to produce CO2. Notice that we have carbon in its zero form, and we have oxygen in its zero valence form as well. So now then this oxygen becomes its standard 2 minus, but we've got two of them, right? See, we've got two oxygens in a 2 minus form. That carbon becomes a 4 plus to be able to work with this. So again, we kind of have a neat little redox reaction here, just as we had a redox reaction up here. So when you have elemental forms of things that react to form something else, that's almost always going to be a redox reaction. So in both of these cases, we have the octet rule that is actually observed. Remember, this sodium up here is an Na dot, or what we've done in the past is I put an X here, right? And we have a Cl that is like so. And then when these things react, this X comes over here to the chlorine. And when it does that, we end up with an Na plus, because now then we have a hole where that X used to be. It's lost an electron, so it's a positive charge extra. And now then we have a chlorine that has that positive charge, so, or that extra electron, so now then it's negatively charged. Notice that this thing has 8 electrons around it. And if you look at the sodium on a periodic chart, it looks like the nearest noble gas because it was in group 1, lost 1 electron, now it looks like the nearest noble gas in group 8 or 18, however you look at that. Lewis structures are kind of amazing in terms of how G.N. Lewis developed this method to simply predict how compounds are formed. He basically said each dot is an electron. So if I have magnesium will be just Mg with 2 dots. Carbon, this is the magnesium's this way because it's in group what? 2. Carbon is in group 4, so, or 14, sometimes you'll see it called. So how many dots does carbon have? 1, 2, 3, 4. Hydrogen is in group 1, so it only has 1 dot. Sulfur is in group 6, or sometimes it's labeled 16, so it has 6 electrons. When you start to put them together and you start using these Lewis structures, it becomes really useful. So you can get sodium chloride, as we've talked about before. You can also get sodium sulfide. Now, with this sodium sulfide, it looks kind of weird, doesn't it? Let's look at this. This structure right here, as I have it labeled, ain't quite right. Is this right? No, it's not right. Let's think about why. If I have an Na that has its 1 electron, I have the sulfur over here that's got 6 electrons, and I have another Na that has its 1 electron. This 1 electron comes over here. This 1 electron comes over here. Now then, I have an Na that has a positive charge here, an Na that has a positive charge here. And what about this sulfur? It picked up 2 extra electrons, didn't it? So now then it becomes 2 minus, doesn't it? So we've got to have those 2 electrons pop in there. Remember, this now follows the octet rule. So now then we have a 2 minus charge on that sulfur, following the octet rule. Here we have no octet. So, what about magnesium chloride? Well, we can have a magnesium donate its 1 electron. This electron, I'm going to make them big green dots for you, to chlorine to make it into a chloride. But what about this other electron? Magnesium, when it still has 1 electron left, kind of looks like it goes from group 2 kind of to this group 1. Not really, but it kind of feels that way because it now has 1 valence electron, doesn't it? So if I move that 1 valence electron down, now what I've got is a magnesium with a 2 plus charge, and each of those chlorines have a negative charge. Do you see how that negative charge tends to get lost? Make sure you don't lose your charges. Okay? That's how you get written up. That was a bad joke if you've ever been in retail. Covalent compounds. This is where we start to use this little, this is what I'm going to call it. We use the NAS method. Okay? So this NAS method. So if I'm looking for methane, okay? And methane is CH4. Okay? How's this going to play out? Well, we could do it where you take, okay, we got this electron for hydrogen. We can add it into the, oh, look, it's kind of hard to see this, but look. There's our little carbon electrons. Aren't they so cute? Oh, lovely carbon electrons. Oh, they're so lovely. So, we have all those carbon electrons right there. And then that hydrogen can join its little electron right there. As Bob Ross would say, it's got some happy little electrons. Well, this thing has to happen how many times? Times 4. And so then that gives us that methane right here. That's the way it's going to look, where you got those hydrogens have donated their 1 electron in, and you've got those carbon that's got its 1 electron that's still floating about it. Now then that carbon has its octet, and hydrogen has its desired 2 electrons. Everyone's happy. Got some happy little electrons there, don't we? Well, if you're looking at it in terms of this NAS method for methane, it'll look something like this. Remember, N means needed. A is what's available. S is what's shared, or if we're looking at it differently, we're looking at bonds. So I have 1 carbon, 4 hydrogens. How do we play this out? What's needed? That 1 carbon needs 8 electrons. Those 4 hydrogens need 2 electrons. You add those two things up together, you get 12. What's available? Carbon is in group 4, so it only has 4 electrons available, while hydrogen's in group 1 and has 1 electron available. So all that we have available are 8 electrons. Now, to get this shared electron kind of thing, these right here, we have got to subtract what's available from what's needed. So we get 4 electrons. These 4 electrons. But if we divide it by 2, that equals I'm trying to see if I did this right. 12. Yeah, I did. So that gives us 4 electrons that have to be shared in between. So if we're looking at this, carbon is sharing 4 electrons, and each hydrogen, if we multiply it out, is sharing 4 electrons. So that kind of works nicely for these compounds. Diatomic molecules, remember, we talked about this. We talked about this in terms of something that I called the what? Diatomic 7. Okay. If I was going to write a comic book, that's probably what I would write. Something on the diatomic 7. When at risk, call on the diatomic 7. So when you have the periodic table, like this, we have hydrogen that's right here, okay? Then over here, we've got some things. We have nitrogen and oxygen and fluorine. And below that, we have chlorine, bromine, iodine, okay? So we see that we have 7, the number 7 on this periodic chart right there, plus 1. When you look at that, those are 7 compounds. Those are your diatomic compounds. These things will form N2 and O2 and F2 and Cl2 and Br2 and I2 and H2 naturally. We have a couple of different ones that show up. You have phosphorus and you have sulfur. Those are directly underneath. So phosphorus becomes P4, sulfur becomes S8. And then the diatomic 7, which are always, whatever it is, 2. That's their elemental form. This is a way that you can look at that in terms of your Lewis structures. Now, I get tired of drawing dots. Whose dot is what? Do I put an X? Do I not put an X? Do I use a color? Do I not use a color? This gets old really quick. And so what I like to do is just say, well, and this is something that all scientists like to do, is I like to say a line. It's easier to use a line than a dotty, as my niece would say. This line basically says that this is one bond. This one bond has 2 electrons. I'm just being lazy and not labeling it as 2 dotties. Fluorine works the same way. We have an F with 1 bond right here, and then we can put all of our dotties around it. See? Now then, if I'm looking at just this right here, I have 2, 4, 6 in terms of my lone pairs, plus 2 for my bond, because it's sharing, gives it 8. Whenever I look at this other one right here, it's the same. Note that we're sharing that bond in between. Okay. You can also have multiple bonds. Okay? That oxygen is a fancy schmancy kind of thing where you can get this double bond. Okay? So you can do that. I'm going to go ahead and show you a double bond and also a triple bond down here. So if I have carbon dioxide, I can have lots of things that happen. Okay? So we can draw all these arrows every which direction and show what's going to happen here. Or I can kind of do it stepwise. So let me kind of do it stepwise and show you. If I have an oxygen that's right here, this electron can come over here and hop into carbon's hole. Whereas if I have this other oxygen over here on the right hand side, we have another oxygen that can pop its little electron right over here into carbon's spot. So now then I have an oxygen here that donated and an oxygen here that donated. One of the interesting things that can happen now is that this electron can donate this way and this one this way. Oh, doesn't that look nice? They just kind of hold hands. This oxygen can do the same thing over here with the carbon. And when that happens, what you end up with is something really, really interesting. You end up with a structure that kind of looks like this right here, don't you? Okay? So, this allows us to say, I've got 4 electrons right here, don't we? That are shared between oxygen and carbon. And I have another 4 electrons right here. That provides us here with a double bond. Easiest way to make those double bonds happen, you connect the dotty-dotties. Isn't that nice? And then we get our final structure over here on the left-hand side. Fascinating stuff, isn't it? Well, what if, let's do something weird. So that's carbon dioxide. What if we use C and we got its electrons, right? So I'm going to put 1, 2, 3, 4. Okay. And we'll have an oxygen with its 1, 2, 3, 4, 5, 6. Okay. So what if one of these comes over here, pops in that hole, and this one comes over here and pops in that hole? Now what do I get? I get this oxygen that's got its 2 here and its 2 here. I have a carbon that's right here, and it's got its 1 here and its 1 here. And what I've done is I've formed a neat little bond in between. So I got a nice little double bond. So that's interesting. So oxygen has its octet, but carbon does not. So carbon monoxide kind of looks weird right now. Is there something we can do to fix that? Well, what if we take these 2 electrons and we send them down here? We have those 2 electrons pop on down there. What's that going to look like? Well, I'm going to copy and I'm going to paste, Because what I want you to see is, if I take those 2 electrons and I pop them on down there, now then I've got this, don't I? And I'm going to take this electron, because it's going to make me feel better to do it this way. If I look here, now then that oxygen has 8 electrons around, doesn't it? Now then this carbon has 8 electrons around it, right? Now then what I've got is this beautiful thing called a triple bond. That looks weird, so I get this triple bond in between. There you go. So it gets complicated pretty quickly with these multiple bonds. Nitrogen also forms a triple bond, which is kind of fun. How's that play out? Well, if I have a nitrogen here and a nitrogen here, and it's got 1, 2, well, let's do it this right. Okay, it's got its 2 electrons right here. It's in group 5, so it's got to have 5 electrons. Each one has its 5 electrons. So this one will play nice with this one. This one will play nice with this one. This one will play nice with this one. And now then what I've done is I've formed a triple bond in between, haven't I? Interesting stuff. There's lots of rules for these Lewis dot structures. Lots and lots of rules. And this is where that NAS method really comes into play nicely. It really, really does. So you got to figure out what the central atom is. That central atom is likely to have the lowest group number. So if you have carbon and you've got oxygen, carbon's going to be in the middle. Do we just see that up here? Hold on, let's see. Oh, look, carbon's in the middle. Beauty. You're going to need to count your number of valence electrons. These are the ones that are available. How do we get those? We see that from our group number, right? Remember, I told you that periodic chart's a great little cheat sheet, right? And then we know 2 electrons are required to form a bond. So try to keep your electrons all nice and connected to get you to an octet. If you don't have an octet in that central atom, you might have to use double or triple bonds. So let's think about this. We can use the brute force method, or we can use this NAS method. So let's think about this one. What if I have, well, let's come down here. Formaldehyde, okay? I'm showing the brute force method here. Can we do it with a more sophisticated method? In this case, notice what we've done using just the brute force method. We take this carbon and we put it in the middle. It's still in the middle, it's still in the middle, okay? So then we'll take these hydrogens and we'll send those hydrogens electrons on down there. And then what we'll do is we'll have the carbon electrons, right? One of them go hang out with oxygen. Okay? And then we need to have the other one go hang out with oxygen. That's what I'm showing in the next drawing right here. So now then, I end up with 4 bonds around a double bond and 2 single bonds around that carbon. And then I still have an octet around the oxygen. Remember, hydrogen likes to have 2. You will find some exceptions to this rule. Hydrogen is one of those exceptions. It likes 2 electrons. Also, helium likes 2 electrons. He likes 2 electrons. Sorry. You find that Li likes 2 electrons. Oy. But beryllium likes 4 electrons around it. And boron is a moron. It likes 6 electrons. So these are all of your octet exceptions in what we call the representative elements. The representative elements, recall, periodic chart kind of looks like this, where you got the representative elements are these right here and these right here. They are the elements in the 2 towers. See Tolkien, for example. So, using the NAS rule to get to the same structure that's right here, we go needed, available, shared, 1 carbon, 2 hydrogens, 1 oxygen. We have that 1 carbon needs 8 electrons, just like that 1 oxygen. But the 2 hydrogens only need 2 electrons. So 8 plus 4 is 12, plus 8 is equal to 20. But what's available, carbon is in group 4, so it has 4 electrons available. Hydrogen's in group 1, so it only has 1 electron available, and oxygen's in group 6, so it's got 6 electrons available. So we have 12 available electrons. When we subtract the available from the needed, we get 8 electrons, right? Divide by 2, we get 4 bonds. Having those 4 bonds, we take the carbon. Remember, carbon is in group 4, hydrogen is in group 1, but hydrogen will never be in the middle, and oxygen is in group 6. So we take the carbon, which has the lowest group number, not including the hydrogen. We put carbon in the middle. We put an H here, and an H here, and an H here, and an O here, because they have to be surrounded according to the way we do these simple Lewis structures. And then here's 1 bond, here's 1 bond, here's 1 bond. I need a 4th bond to make that carbon have 8 electrons. There that is. I've got 12 total electrons that are available, and I'm showing 8 electrons right now. So what I need to do is add 4 more electrons. 1, 2, 3, 4. There's those 4 electrons. This gives us our 12 that's right here. And I'm done. Sometimes the NAS seems to work a little bit better. A little faster, more efficient. All right. You also have something called resonance. Resonance is fascinating. So we have ozone in this old world, and ozone is an allotrope of oxygen. Allotrope means it's comprised of the same type of elements or elemental composition, but it's a different form of that element. So graphite and diamond are both carbon, but they have different forms. No one's going to get a big, huge rock of coal as a engagement ring. And if they do, you should dump the boy. I'm just saying. You need a diamond there, not a big old chunk of coal. Now, when we do these Lewis structures for oxygen or ozone, it gets interesting. So let's see how this works. We're going to try a brute force method, and we're going to try the NAS method. So if I'm looking at NAS, what's needed, what's available, and what's shared. Okay, if I have 3 oxygens, those 3 oxygens need 8 electrons each, but what's available is 6 electrons. So that means I have 24 and 18, and when I subtract the 2 one from another, I get 6 electrons. If I divide by 2 to figure out, because you got 2 electrons per bond, that gives me 3 bonds. Who's going to go in the middle? Oxygen, oxygen, or, hold on, oxygen. Let's put an oxygen in the middle. Okay, great job. So where are we going to put the other oxygens? Okay. Let's do it. Now then, what am I going to do? I got to draw 3 bonds. Well, I can put 1 bond here and 1 bond here. Great job. But I got to do another bond. Where am I going to put the bond? Well, I could put the bond over here. But I could also put the bond over here. But I could also put the bond over here. But I could also put the bond over here. So we get something weird that shows up. We get this neat little thing where now then I can put this bond on either side, can't I? There's not a whole lot of difference between the two of them. You can flip-flop back and forth, can't you? Interesting. So now then that we can flip-flop these things back and forth, we got to put the other electrons, right? I'm showing 6 electrons. I've got how many electrons? I've got 18 electrons I've got to show. Where's the other 12 electrons? Well, to begin with, I need to put 2 electrons in the middle. And if I do it to the left side, I got to do it to the right side too. Okay, now then that middle has 8 electrons. Whew. So let's start dealing with the left-hand side first. Forget that you have the right-hand side. You might put a hand over it. I don't care. So now then, to get an octet of electrons on the right-hand side, I think is what I said you need to fiddle with. Let's put some pairs there. So now then, if I'm looking at this, what we've got is, yes, this thing here has, I'm showing 8 electrons, right? But now then, that's for the middle. For the right-hand side, that now shows 8 electrons as well. So far, so good? Just on that left molecule. Can I get another batch of electrons and use them to get 8 electrons? How would I get over here 8 electrons? Is there a way that I can do that? Well, if I do 1, 2, 3, 4, 5, 6, 7, 8 in that bond. So now then I have 8 electrons on each of those oxygens, don't I? Let's count the number of lone pairs I've got on these things. We'll go with lavender today. I've got 1, 2, 3, 4, 5, 6. That's 12. Remember, I had 6 electrons right here. And I've got 12 left over, right? That 12 that's left over are in those of lavender. These 6 right here are in the 1, 2, 3 bonds. So now then, we can redraw this on the other side where it's kind of a mirror image. So the question is, what's really the difference here? Well, you can actually label these things differently. So I can label this one as a dark blue, and it's this one that stays dark blue. I can look at this, and if I labeled the one side, what happens is I'm actually changing things. So what this shows is I have a resonance structure. These are two equivalent Lewis structures. They're absolutely identical in every way except for the label that I've got now. So these are resonance structures. And what really this kind of looks like, when you look at this thing, what it really begins to look like is where you've got an oxygen here and an oxygen here and an oxygen here, and you've got a bond here and a bond here, and you got kind of a half bond here and a half bond here, because it can go back and forth and back and forth and back and forth and back and forth and back and forth. So ozone looks kind of interesting. Notice I didn't draw the complete Lewis structure for this molecule. I'm just kind of showing you this becomes a, and I'm going to put the lone pairs right here. This becomes a resonance hybrid, which becomes important later on. This allows for ozone to work to remove the harmful UV rays out of our atmosphere so we don't get cancer from the sun. Those are resonance forms. Resonance hybrid is where you have kind of this ozone that is kind of a mixture of a couple of different structures. I've already shown you that. Don't worry about the pluses and minuses at this stage. Now, what's interesting here is as we progress, you begin to find that there is a valence shell electron pair repulsion theory that factors in. These Lewis structures talk to us about how electrons can be counted and how structures might be predicted in terms of number of bonds, but they don't tell you anything about the structure. So we use something called valence shell electron pair structure. Let me kind of lay this out for you. If I have a human that's here, and this human is going to be talking to this human here. Okay? So they're going to converse one to another. Looking at the center body to here, they're going to talk straight at each other like this. This is how two humans tend to communicate. Now, if I add a third human into the mix, so I get a third human that begins to walk up this direction, okay? So I'll kind of do this in an interesting way, okay? I think it's interesting. This third human go, he's going to try to step in here to converse with the both of them. But if he only wants to converse with one, he'll step into the one side. But if we're trying to have three things be present, what's going to end up happening is they're going to communicate like this. And now then, this guy is going to communicate where they kind of face each other, all three, looking at center mass. That being the case, now then we get this neat little form of three. What happens if a fourth comes in? That's an interesting thing. But let me ask you this. If this person right here needs to come in a little bit closer. Isn't it going to kind of split up the other two? They're going to kind of be pushed back a little bit. So what happens is we don't have just a person, but we got a couple that are attached at the hip. You know how that works, don't you? So this couple now comes up in here. They require a little bit more room, don't they? So the other two have to spread out a little bit. And in order for them to spread out, to give the couple room, something has to give. So what happens is, if we have something that looks like carbon dioxide, where we have a carbon that's double bonded to an oxygen that's double bonded to another oxygen, like this, now then, to give these double bonds the most room compared to this double bond, we need it at 180 degrees. So now then, we have this nice little linear form. Well, what if we have something like that ozone? So I have an oxygen here, and I've got that couple that's attached at the hip. Remember? They need that extra space, so it kind of spreads things out. So what happens is it spreads this double bond and this single bond in such a way that we get a bend here. So now then we get something that is a little bit less than 120 degrees. It is now bent. Well, if it's not an actual complicated thing, so let's deal with BF3. I'm going to draw the structure real quickly so that you can kind of see. Remember, boron is a moron and only likes 3 things to be bound to it, okay? Now then, what you see is this angle that I have right here is right at 120 degrees, and it's something called trigonal planar. Because when we converse in a group of 3, or 3.5, because there's someone who's kind of attached at the hip, needs extra room, then we get pretty close to that 120 degrees. Now, it gets a little more complicated whenever you add a 4th thing. And I'll talk about that momentarily. So we find out that these pairs of electrons repel each other. Why would a lone pair repels more than a bond? Well, quite frankly, that lone pair isn't shared. This bond is shared. So if a lone pair isn't shared, that means we got 2 electrons with this negative charge right here. 2 full negative charges right there. Whereas in this bond that's over here on the right-hand side, it's not 2 full-on negative charges. They're shared. They're split up between 2 different atoms. And so they don't need as much room. Okay? Now, what's interesting here is whenever you start to look at what happens when you look at things in 3 dimensions. In 3 dimensions, what we find is you get 4 points. Those 4 points end up showing something interesting, where you can put a central atom right here in the middle. When you put that central atom in the middle, what you find is you can have a bond that's right here to this point. You can have a bond that's over here to this point. And if you look, those are in the same plane. The dot on the far left is in the same plane as the dot on the far right. But what happens is you have the dot that's kind of up here in the middle. It's kind of pointed out at your face. So what we do for something that's like that, we actually draw something called a wedge. That wedge kind of says, this thing's pointed out at your face. That carbon is right there in the very middle. That central atom is right in the very middle of all of this. And then what we do is we draw some hash marks to show something in the background. So this yellow dot, the one with the arrow, is pointed out towards you. So if we're going to show this kind of neatly, if you will, it's going to be much bigger toward your face, won't it? Whereas the dot that's back here will be much smaller than the others. To draw this outside of here, I'm going to show you it a little differently. So if I have a carbon, because carbon likes 4 bonds, then I can put one there, and then you kind of don't make the perfect triangle. You kind of make it a little bit whoppy-jawed, as my wife would say. And then you do this thing. So now then it begins to look like we can have a hydrogen sticking up and a hydrogen sticking out and to the right. We can have this hydrogen sticking out at your face. And we can have this hydrogen that's kind of in the background over here. Now you can start to see the tetrahedral come into shape. So this bond angle that's right here is 109.5 degrees. That's what you have when you have the tetrahedral form. Now what happens if we do something a little bit wonky? Okay, you ready? We like wonky, don't we? Aye, we like the wonky donkey. So what if I have a nitrogen? Nitrogen likes to have 3 bonds. So let's put a hydrogen here, and a hydrogen here, and a hydrogen here. If we do the NAS, we find that there's a lone pair that's right here. So now then, this lone pair that's up here, this thing is pushing down on all of these different bonds. And so we find that the bond angle that's right here in the middle is less than 109.5. And so while we have methane over here that is in a tetrahedral form, we now have ammonia in the blue that is actually, it kind of looks like a pyramid, right? So it's pyramidal, but specifically looking at those H's that form a triangle, it becomes trigonal pyramidal. Well, what if we get a little bit more complicated? You ready for this? I don't know if you're ready for this. Y'all ready for this? Oh. Y'all ready for this? You have to go look it up. It's from the 90s. Oh. If I have an oxygen, as in water, Water's form looks like this. Remember, I said it kind of looked like this a couple of weeks ago when we were talking about solutions, I think, mixtures. So now then, I've got those two lone pairs. This lone pair pushes down just like this lone pair pushes down. But this lone pair also pushes this way, and this lone pair also pushes this way. Because one of those lone pairs is pointed out at your face, and the other one is pointed into the board. So as a result, the bond angle that you get right here is much less than 109.5. In fact, the bond angle for water is on the order of 105 degrees, whereas the bond angle for ammonia is about 107. So it becomes pretty significant. See how it plays out. Why am I talking so much about these bond angles and all this other kind of stuff? Well, it's pretty straightforward. Because if ammonia looks like this and is trigonal pyramidal, while water is bent, now then we get this polarity that happens. Remember when we were talking about polarity? We said if something is more electronegative, so let's think about this. I got my periodic chart up here, right? Electronegativity shifts from francium up to fluorine, okay? Francium to fluorine. Remember, we don't talk about the noble gases. As a result, hydrogen is in the top left, oxygen is right next to fluorine, so we find that we have a pull right here of oxygen from the hydrogens. So the hydrogens become delta positive, while that oxygen becomes delta negative, and we have a big, huge pull, kind of like a tug of war, toward the top left as I've drawn it. Well, with the trigonal pyramidal form of nitrogen, who's next to oxygen, we find that hydrogen gets a little bit pulled on as well. Not quite as much as oxygen to nitrogen, but we still see a pretty decent pull forward, where this nitrogen is delta minus, and each of these hydrogens are delta plus. When we have formaldehyde floating about, let me draw formaldehyde here, which we drew last time or so, where we have a pull like this, because oxygen is delta minus and that carbon is delta plus. Now then, what happens is this lone pair, we'll do it this way, this lone pair right here comes in and wants to react with the formaldehyde. And if what we've got is this nitrogen, this ammonia, what if this ammonia is attached to a protein? We have a free base on that protein. Now then that protein can react with the formaldehyde, and we can begin the process of embalming. Wow, all that just from the structure of simple molecules. So, fascinating stuff, isn't it? Here's another picture of methane for you. All right, we already talked about electronegativity a couple of times over. Remember, fluorine is the most electronegative, francium is the least. That means if given a fight between francium and fluorine, francium is going to lose. Fluorine's going to take its electron, no ifs, ands, or buts. Francium has no chance. The polarity is additive, Remember, polarity of bonds is additive, much like a tug of war. You ever do one of those tug of wars where you got the circle in the middle and you got a rope this way and a rope this way and a rope this way and a rope this way? And what you're trying to do is get this circle to move past a certain point. If you've done that, you win. You're working against 3 different teams. So that polarity is kind of like being pulled in this tug of war. Fluorine's going to always win if given a choice. Okay? With that, I'm going to wrap up my bonding. I hope you feel much more bonded to the subject.